Good morning. I am Shailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today, I am going to discuss generalized impedance converters and basics of the filters. As the name suggests, generalized impedance converter is a type of circuit which can convert impedance, or you can simulate, you can obtain whatever impedance you desired. You can obtain impedance of any value, you can obtain resistance of any value, you can obtain capacitance of any value, you can obtain inductance of any value, whatever value is desired or whatever value is required. Even there is one most important aspect of this circuit, that is, in electronics, generally we used to avoid the use of inductors because inductors occupies large space, they occupies large area, and there are many examples where even whole chip will not have that much size, or whole chip will have very small size, and even a single inductor will occupy more space. So, generally we used to avoid the use of inductors. But by using this circuit, soon you will come to know that we can realize inductor without using inductor actually. We can obtain inductors, we can obtain the response of inductors with the help of capacitors and resistors. So, this is the most important aspect of generalized impedance converter. So, let us analyze this generalized impedance converter circuit. See, we have taken 1, 2, 3, 4, 5 impedances Z1, Z2, Z3 and Z4 as well as Z5. There are two amplifiers. One is A1, another is A2. Now, to find out the overall impedance of this circuit, we will put one dummy voltage source V, and due to this voltage source we will find out the current I which is flowing into this circuit like this I. And finally, we will find out the ratio of V and I, and that will be the overall impedance of this circuit. This is which we will do, which we will analyze in this circuit. See, we have connected two amplifiers. Now, see, let us consider that the voltage of this point is V, because this is V. Then potential of this point will also be V. Again, the potential of this lead will also be V via virtual short circuit concept in operational amplifier. If this is V, then this will also be V. If this is V, then this will also be V via virtual short circuit. Let us consider that this is V2, which is connected here, and we have considered that the output of this is V1, so this is V1. Now, we will find out current in each and every branch. So, let us check Z1 and the current across Z1, and the current across Z1 will be equal to this voltage V minus V1 divided by the impedance Z1. So, I will be equal to V minus V1 upon Z1. Now, again apply the KCL at node C, at this node. So, I1 will be equal to I2, and I1 will be equal to potential of this point, that is V1 minus V upon I2 is V minus V2 upon Z3. So, V1 minus V upon Z2 is I1, and V minus V2 upon Z3 is I2, and you know that we can write V1 minus V upon Z2 as from this V minus V1 upon Z1 is I. So, I is equal to V minus V1 upon Z1, or we can say that V minus V1 is equal to minus I Z1 So, simply by this equation you can put the value of V minus V1 and V1 minus V is equal to minus I Z1. So, you can write here, put value of V1 minus V, that is equal to minus I Z1 upon Z2. Z3 will move here and you will get Z3 is equal to V minus V2. So, you will get it. So, now you can say that V2 is equal to V plus I Z1 Z3 upon Z2. From this equation you will get it. Now, again apply KCL at node E, and node E is this, and you can simply say that I3 is equal to I4 and I3 is equal to V minus this V3 minus V upon Z4, and I4 is V minus 0 upon Z5. So, you can simply say that V2 upon Z4 is equal to V upon Z4 plus V upon Z5. So, again you can write V2 is equal to V into Z4 plus Z5 upon Z5. This is equation number 3 and this is equation number 2, and both equations are in terms of V2. These two equations are in terms of V2. So, we can obviously we can compare these two equations and we will get V plus I Z1 Z2 upon Z3 upon Z2 is equal to V Z4 plus Z5 upon Z5. So, V is on this side. So, you can take current terms on right hand side. So, it will become minus I Z1 Z3 upon Z2, and you can take this V term on left hand side. So, it will become minus. So, you will take V as common, you will get 1 minus Z4 plus Z5 upon Z5. If we will take LCM, we will get Z5 and on this side Z5 minus Z4 plus Z5. Actually, if it will multiply by minus, then it will become minus. So, it will be cancelled out and you will get minus Z4. So, this term will be modified as minus V Z4 upon Z5, which is equal to minus I Z1 Z3 upon Z2. So, from this you can simply write minus minus will be cancelled out and V and I will come here. So, V upon I is equal to Z1 Z3 Z5 upon Z2 into Z4 and earlier I told you that overall impedance of this circuit will be equal to the ratio of V and I. So, Z is equal to V upon I and Z will be equal to this Z1 Z3 Z5 upon Z2 Z4. This is the impedance that this circuit will offer, and it is very easy to remember this. You can remember this expression Z is equal to Z1 Z3 Z5, that means odd impedances towards numerator side, and if you will observe the denominator impedances Z2 and Z4, these are even impedances. And earlier I told you that you can simulate inductor with the help of generalized impedance converter. So, let us see how we can realize inductor with the help of capacitor and resistors. Let us consider Z1 is equal to R1, Z2 is equal to C2, Z3 is equal to R3, Z4 is equal to R4 and Z5 is equal to R5. You know by Laplace. L is equivalent to SL. This is C and this is R. So now if you will put these values in the expression Z, you will get R1, R3, R5 upon R4 into SC2. So you will get this, and any impedance which is like this, response of inductor. So from this, if you will eliminate S, then you will get the value of L, inductance. So Z is equal to SL. So L is equal to R1, R3, R5 into C2 upon R4. So whatever value of inductor you want to obtain, you can put here, you can solve this expression and simply you can obtain that value. Is the filter. So we will briefly see what filters are. However, many of us have idea about filters. We may not have actual idea of the filters which we use in electronic circuits, but we are familiar with the word filter. Filter is something that passes something and stops something. Similarly, in case of electronics also, filters are the electronic circuits that can pass some frequencies while they will stop some other frequencies. Depending on this, filters are categorized as low pass filter, high pass filter, band pass filters and band reject filters. Actually, there is no mechanism, there is no device which can fully or instantly or after any particular frequency can stop all the frequencies, and before that it will pass all the frequencies. Rather than this, there is a mechanism, that is, this circuit will attenuate frequencies, and but we cannot say that for the frequency of 1 kilohertz it will pass, at the frequency of 1.1 kilohertz it will fully stop the signal of that frequency. No. The reality is attenuation increases or decreases. When attenuation will be very high, we can say that it has stopped all the frequencies. If attenuation will be very less, then we will say that it will pass the frequencies. So if you will check the response of filters with respect to frequency, then filter may have response like this. For example, this is the response of low pass filter, and this response says that as the frequency increases, attenuation increases. Or in simple words, we can say that this filter will pass all the frequencies which are in this range and it will stop all the frequencies above this. So most popular RF filter topologies are 4 type of topologies. One is the Butterworth filter, Chebyshev filter, Bessel's filter and elliptic filter. So I will compare here all 4 type of filters. You can see this is the Bessel's filter. Bessel's filter have very less roll off, and we want that roll off should be high. And after this we have another response, that is Butterworth. You can see this is the Butterworth response. Its roll off is more than Bessel. And in case of Chebyshev, roll off is more, but it will introduce ripples in the passband. And elliptic filter will have more roll off, but elliptic filter will introduce ripples in both passband as well as stopband. So it depends on the application which type of filter you want to choose. Now active and passive filters. The filters or the filter which will use passive components only, like RLC components only, will come under passive filters, while active filters are those which will be designed with the help of passive filters as well as which is designed with the help of passive components as well as active components, like RLC and operational amplifier, or BJT, means there must be at least one active component for the designing of active filters. Filter can be called as active filters only if that filter will contain minimum one active device. Just like passive filters, active filters are also categorized as low pass filter, high pass filter and band pass filters. And low pass filters are those which passes the frequency less than some particular frequency, like this. If this is F, this is amplitude. If this is cutoff frequency, it will pass all the frequency. So this is low pass filter. Another one may be high pass filter. The filter which will pass the frequency is more than cutoff frequency, it will come under high pass filter. Band pass filters are those which will pass the band of frequencies, like this. For example, this is FC1 and this is FC2. Means the frequencies between two cutoff frequencies we will obtain at the output. This type of filter will come under band pass filter. And band reject filters are those which will stop the frequencies between two cutoff frequencies. For example, this filter, it will stop all the frequencies between these two, while it will pass before this FC1 and after FC2. So this is what we have to discuss today. In next lecture we can discuss filters in detail. Thank you.